Hello and welcome to Lecture 6 on Schrödinger's equation. This is the lecture to prepare you for Topic 6, and it's meant to quickly introduce the topic, cover some concepts, but also prepare you for the associated homework assignment, the homework packet. All right, let's jump right into it. So we're talking about Schrödinger's equation, which we'll soon learn the details of. But first, let's talk about what are matter waves. A matter wave is a small piece of matter, a small particle that has noticeable wave-like behavior under certain conditions. The best candidates for matter waves are electrons, and then followed by other common particles, and also protons, neutrons. So we're talking subatomic particles and electrons. So what the wave-like behavior is best known for is to have a wavelength and to behave like a wave in terms of refraction, so bending when the particle passes through a change in medium, but most importantly, diffraction, which is what we see right here, which is a diffraction pattern happening when a electron passes through a single opening, in this case, a circular aperture, and we see that characteristic interference pattern because of different wavelengths arriving out of phase and canceling each other out in the case of dark spots, right? So, and then constructively interfering where we see our light bands. All right, and this wavelength that's associated with matter waves, so this is any particle that has a wave particle duality, is the de Broglie wavelength shown right here. And the de Broglie wavelength is related to the properties of the particle entirely through momentum, where momentum is just P equals mv for non-relativistic particles, just classical momentum, mass times velocity. H is Planck's constant, and that's going to be the quantization of these waves. Because it's associated with quantum mechanics and splitting things into the smallest possible pieces. All right, so we have a quick example here. We're asked what is the de Broglie wavelength of an electron with a given kinetic energy in electron volts. We're then going to take our ideas of momentum and kinetic energy and then rearrange our equation. Basically, use these formulas to relate kinetic energy to momentum and then solve for momentum. That's because we were given kinetic energy rather than being given momentum directly. But now that we have it, we can use the de Broglie momentum, that is. We can use the de Broglie wavelength formula and go ahead and solve and find out that the wavelength of this particular electron is 112 picometers, so just a little bit less than a single nanometer. All right, so kind of actually on the scale of an atomic nucleus radius, which is an angstrom and equal to 10 to the negative 10. This is a fairly high energy electron, and different energy electrons would have different momentum associated with them. So essentially the velocity, the kinetic energy, the momentum, however you want to think about it, is going to set the wavelength. Okay, and this could even be compared to light. And perhaps about a light energy that's carried for the equivalent wavelength. Because photons, although they're also particles and waves, they do not have a de Broglie wavelength because their wavelength is directly related to the speed of light, whereas all these other particles can have various speeds. That is the key difference between the two. That is the key difference between photon wave particle duality and anything that has mass, such as an electron wave particle duality. Although there's some similarities, some key differences. But that's not our focus today. Instead, our focus is all about matter waves, which is why we introduced the de Broglie wavelength and the concept of matter wave diffraction and so on. So let's get right into it. Let's talk about Schrödinger's equation. What are we going to do with this equation? Why are we working with it? Well, the equation is shown right here with some nice labels attached to it. We can see that there are two terms on the left and they're equal to a term on the right. This is the most general one-dimensional form. In a three-dimensional form, we would have partial derivatives and x, y, z. And I say it's the most general form because it includes time dependence. And that is not going to be something that we're going to see in any examples. You won't see any time-dependent waves in any assignment that you will likely see in any physics class. It's considered pretty high-level math. and it's not particularly easy to work with. So we're going to be, no surprise, trying to think about what we can do with matter waves where there is not a time-dependent behavior. But more on that in just a second. Since this is the Schrodinger's equation, and we might want to take a minute and think about what that really means. What does it mean for it to be an equation? Well, it's a differential equation. All right. Now, don't worry. We're not going to have to do anything that you would learn in a class on differential equations. In other words, you do not have to have taken differential equations to understand everything that I will talk about. Rather just think of this as an equation like x plus y plus z squared equals 10, or something like that. And we just need to then find out what is our solution. In fact, it would be more like x plus x squared equals 10. In that case, of course, we use the quadratic formula to solve for x, because this equation, just like an equation with a single variable, has a solution. But unlike an equation with a variable x, for example, this equation, the Schrodinger's equation in this case, which is an example of a differential equation, well, its solutions aren't just letters, they're functions. And that's what we see right here. We see that the wave function, shown below, right here, is the solution to the Schrödinger equation. I shouldn't say the solution, it's a solution, all right? Because there are actually different functions that in basically every common case that will give you a solution to the Schrodinger's equation. There's not every function is going to be a valid solution. It has to actually work. We have to be able to plug it in and have this equation be true. And if you think about what it would be like to test that this is indeed a valid solution for the differential equation or for Schrodinger's equation, we would plug in this whole expression here every time, because you can see that it's this term right here. So every time we see this function of x and t, we would replace it with this expression here. So we'd plug it in here and here and here. That would involve taking its second derivative in the case of the term for this on the left, just plugging it in without taking any derivative. In the case where it's multiplied by potential energy, expressed by U as a function of x, and then just taking a single derivative with respect to time on the term on the other side. Okay, so second derivative with respect to x, one derivative with respect to time, plug it all in, and you'd find that indeed it's true. It'd be a true statement. The equality holds. So that's the idea of the wave function being a solution to the equation. All right, so there's three main takeaways that I want you to think about over the next 3 slides, okay? These are the 3 takeaways from Schrödinger's equation. Number 1, probability and waves have a surprisingly strong connection. So I haven't mentioned the word probability yet, but I'm just about to, and I don't want it to seem like it comes out of nowhere. Probability is integral, for lack of a better word, understanding this topic and understanding what we're actually going to do in terms of measurement and specific situations with Schrödinger's equation. Okay, you can think of, in fact, that the idea of Schrödinger's equation, or rather, the idea of probability, is what is the bridge between the wave and particle nature of any wave-particle duality. So, this idea that electrons aren't really particles, but they're not really waves either. They're both. That's what's called the wave-particle duality. Well, to bridge that gap and to make sense of what measurements you would take and what physical reality we're thinking of, probability is a really, really important bridge. Okay, and we'll also mention why it's almost necessary to even make sense of any real life result. Okay, for a quantum mechanical system, which if you kind of lost track of what the quantum mechanical system is, it's just anything really small. So if you were to continue with kind of building on these topics and move over to more complex integrals, eventually spherical coordinates, this would be in service to setting up the quantum mechanical hydrogen atom and finding the solutions for the energy states of the electron that's trapped essentially, because of its potential energy pull to the atomic nucleus. Okay, we won't go there because we're going to stick to linear systems and less complex, and that's more of a course in quantum mechanics to arrive at such a detailed solution. All right. Well, our second main takeaway is that the particle's situation tells us which version of the equation to use. Okay, so we just saw the most general version. So that would be, I guess it would apply to just about everything, but it would be overkill. And as I said, very difficult to work with. There are going to be many other types of conditions that can be covered. There are oscillators that we can discuss. There are the idea of trapped particles that are not completely trapped, and so on. And so when we talk about all these different types of situations, that tells us what version of the equation to use. So think of that as a heads up that there are going to be different versions. Ultimately, we're going to arrive at one version that is going to be used exclusively in the homework, and it's going to have itself a 1D case, a 2D case, and a 3D case, but it's still one version of what I mean here. It's one particular type of the Schrödinger equation. All right, so we'll cover that in a minute. And finally, the third takeaway is that you only really care about the size and shape of the prism. And the prism is the particle's prism, because the special situation that we're talking about is trapped particles. All right, because I said, we're only going to, that each situation has its own, version of Schrödinger's equation. Well, it turns out that the version that can be solved directly through integration, that has kind of, maybe perhaps the easiest to work with, one of the simplest cases, all right, is going to be the case of a particle, usually an electron. That's kind of the most realistic thing to consider. And that electron is completely trapped. It can't escape whatever confines we set for it. So it's an inescapable prism, and I'll clarify what that means as well. All right, so with that kind of heads up about what to keep an eye out for, let's get into our definition here. So Schrödinger's equation, what is it? Well, before we talk about it, let's go to the wave function. If you remember from 2 slides back, that's the solution to Schrödinger's equation. So we're starting with the solution, and we'll go back to the equation. So if a wave function, defined as the letter psi, as a function of x, y, z, and t, can be used to describe matter waves, then its space and time variables can be grouped separately and can be written in the following form. We saw that as when I said, hey, this wave function is a solution, you saw that same separation. Where omega is just the angular frequency of the matter wave, because the wave can be defined in terms of a frequency, a wavelength, an angular frequency as all three, just like any mechanical wave. It's probably not the only time I'll say that, although I'll try not to repeat it too much, that Schrödinger's equation and the solutions, which are the wave functions, they do describe waves, and those waves follow all of this same rules for waves that would be set for a wave on a string, a sound wave, an ocean wave. So all the ideas apply equally. All right. So let's suppose that a matter wave reaches a particle detector, then the probability that a particle will be detected in a specified time interval is proportional to that wave, the matter wave function, or just the wave function, squared. All right. So we're squaring the wave function. We're taking the absolute value and we're squaring it, but just squaring it will take care of any negatives. Where the absolute value of the psi function is just defined in the typical notation, and this wave function squared, or absolute value of wave function squared term right here, it is always both real and positive. Okay, so that's going to be a key idea, because that is an interesting sort of bridge between, or the bridge, in this case, it's the bridge between mathematics and physics, because as you probably noticed, when we had the general solution, there was I for the imaginary number. So that's great in terms of being able to solve some of these functions, but imaginary numbers don't have any physical meaning. So when we actually look for something that can be physically measured, we have to make sure we're only looking at the real part of it. Not necessarily positive. There are cases where we might be interested in something negative, but real, right? And that actually happens a lot with some of these fields of physics, that you have a solution method that involves imaginary numbers, but when you finally get to a value that could be measured, a physically real value, it can't have imaginary numbers. All right. So the last point here in the blue box, the probability per unit time of detecting a particle in a small volume centered on a given point in a matter wave is proportional to the value of that psi squared function at that point. Okay, so what that's hinting at, and we'll see it explicitly said in just a second, that means that this square, or absolute value squared of the wave function, is associated with probability. In fact, it's called the probability function. Okay, so let's dig into that idea. Okay, so Schrödinger's equation, matter waves are described by Schrödinger's equation. That's the idea. This is a descriptive equation. It's like it's these a lot of these differential equations that you see in fields of physics. They kind of define a whole like a whole kind of subfield of physics. This single equation can be used so many different times and has been. And so it's like the most fundamental way to mathematically start with the subject of matter waves. All right, it's meant to be a complete description. That's why the full form is so impractical to actually work with. That full form we saw when we first saw the equation. Suppose a particle traveling in the x direction, just reading here, through a region in which forces acting on the particle cause it to have a potential energy, U, as a function of x, right? So that'd be a one-dimensional potential energy function. In this special case, Schrödinger's equation can be written as, okay? So this is a case where we have time, rather we have time independence, right? So we're not worried about anything changing in time, okay? Furthermore, we have a potential energy term and we've got a total energy term, which is the E. All right. So it might make sense to put the E on the other side, and sometimes it is written there. So you're thinking of it as one term plus, imagine distributing over here, another term. When you add those two terms together, you get total energy. But if you move everything to one side, that's like kind of almost a way that we think of energy conservation, like we would do with the second law of thermodynamics, the first law of thermodynamics, where we say that we have all these different energy changes, but the net change has to be zero. So the idea here is that total energy, we might think of it as being kind of part of the system, and then as we have to add everything together, it has to sum to zero. And it just really represents energy conservation. That's all. That's why it's set to zero. For a free particle, U as a function of x is zero. Okay, so this is one of those situations where we refine the equation, right? So we're gonna modify the equation. We already have, because we've gotten rid of time dependence. So that's looking at what type of situation we want to look at, and simplifying or just changing Schrödinger's equation. And then even more, and certainly mathematically a major simplification is setting this whole term to zero. All right. So we're just saying that imagining a system with no potential energy. It's like it's the kind of the gravity, the equivalent in gravitational potential energy would be being so far from any other source of mass that there's just no tug from any gravity. That would be a gravitational potential energy of true zero, just a completely open space. And that's the free particle idea. That equation, this case where U of x is set equal to zero, describes a free particle where a moving particle, describes a moving particle, right, on which no net force is acting on it, right, because otherwise there would be potential energy associated with that force. The particle's total energy, because it must still have energy, and we didn't say it was at rest. In fact, it wouldn't make sense for it to be at rest. It wouldn't be anything to define, because it wouldn't have a wavelength if it was at rest. It would just have a rest mass, but that's a topic for special relativity. But anyway, the particle's total energy in this case is all kinetic, okay? So E is kinetic energy. And that means that we can just go and set E, as written in the equation, just equal to non-relativistic kinetic energy, and then plug that right into the equation, as you can see, and then simplify things, and we've got a nice new version of Schrödinger's equation. All right? So situation defines the version of the equation. The solution, right, because it's a differential equation, to this particular version where there's no derivatives with respect to time, there's only a second derivative with respect to x, and then just a linear term. The solution to it is this sum of exponentials, and it is indeed related to trig functions as well. It's I believe it's called the Euler's identity, and it's we have a imaginary term, or actually both terms have an imaginary. Both terms are imaginary, but when you actually plug them all in, you would lose your imaginary term, all right, which you can see being done over here. And I should be more specific, plug them into what, right? Because if you just plug them into the equation and maybe check that the solution works, and that is a common type of problem, that you would see like in textbooks. It's not something that you're going to see in the homework assignment that this video is preparing you for, but it is common to assign students to say, hey, plug this function in and make sure that it really works, which is good practice in algebra and just good reassurance that this is what we're actually talking about when we say that it is the solution. You just plug it in, and indeed in this case, make sure everything cancels and sums to zero. But the point being is that that's not really how you make physical sense of it. I said that you have to lose your imaginary terms in order to have something that is physically meaningful, and that often comes down to looking at the probability. Okay, so here, if we wanted to find the instantaneous position of the particle, it wouldn't really make sense because it's just a free particle. Its position doesn't mean anything. There's no potential energy, so the coordinates aren't special. It just has kinetic energy everywhere, and everywhere doesn't change. It's just in some vast void of a vacuum somewhere, this particular electron. Okay, so it doesn't make sense to really talk about instantaneous position or anything like that, or instantaneous velocity for that matter. Furthermore, the thing that we're going to look at always for physical relevance is going to be that probability function I mentioned, the one that is the absolute value squared of the wave function. Okay, and you can see here that if you take the solution and you go ahead, so if you take the wave function, which is the solution, and you go ahead and find the probability function by taking its absolute value and squaring it, then you get a final result, just a constant. Okay, so you actually get a value, a measurable value. Okay, so that's what we're going to be doing. That's how we're going to think about the Schrödinger's equation for the context of your homework, is you're going to be interested in probabilities. Okay, now let's extend that a little bit to perhaps where it matters even a little bit more. Okay, now that's kind of a quick context to that, or maybe a further justification of why we care about probabilities, is something called Heisenberg's uncertainty principle. Because Heisenberg's uncertainty principle tells us that particles that are small enough where they start to have values that push up against Planck's constant, okay? So in this case, we're looking at products of the particle's position and momentum. And the reason we have a change in position and change in momentum is because it represents an inherent uncertainty. Because the product of some delta, think of it as almost like an error bar on a measurement of x, which would be the position of the particle, and then the delta p in the x direction. Well, that would represent the error bar on a momentum measurement, where again p just equals mv. Okay, so the product of those two physical quantities can never be less than h bar. And what is h bar? Well, it's just Planck's constant divided by 2 pi, and it comes up so often that it's helpful to not always write h over 2 pi. Instead, we just write h bar. It's a shorter way to save ourselves a few lines. Okay, but this interesting fundamental property that we're not going to show a derivation for, it tells us something. It tells us that particles can't be really, exactly confined. And well, that maybe I shouldn't use the word confined because I'm talking about particles being trapped in boxes. It's more like they can't be exactly defined. It's the particle. You can know something about it. You can know its position very, very accurately. But the more accurately you know its position, the less accurately you know its momentum, and vice versa. And as you can see, it's also related to any direction of it's not just x. And because of that, because the exact position or exact momentum is inherently uncertain, it makes us think, well, then how are we going to evaluate the system? We're not going to be able to define its instantaneous value like you would for a wave on a string, or define the instantaneous value of an oscillator, right? In those large scale mechanical systems, it makes sense to be like, well, what is the wave doing at t equals this, or what is the wave doing at x equals that, or perhaps both x and t being specified? Well, that just doesn't make sense here, because it's not going to tell you something that you really could know. So why would you ask it? So that then leads to this idea, well, then what can you ask? Well, you can ask for the probability of finding the particle somewhere. So that's going to be the questions that we're going to be asking for these tiny, you know, particles that obey the laws of quantum mechanics, where things can only be split down into quanta, the smallest possible sizes of energy and space and so on. Well, in those cases, you have to like give up a little bit of certainty, and you have to instead say, well, I know I can't know exactly where the particle is, but what's the chance that I find the particle, over here in this part of the room, or or this part of the box, or this part of the wire, right? This part of the defined system. And that wouldn't have made sense for the free particle, because the free particle is a case where the particle isn't really anywhere specific, because it's just in like a black room where everywhere is the same as everywhere else, right? But now we're going to be talking about cases where it's not just a undefined system. It's a box or a corral, which is the two-dimensional name for a trap, or essentially like a one-dimensional trap, which is like a wire. In all of those cases, that you want to actually think about where the particle is, but not just like its instantaneous value, but instead the chance of it being in the middle or the chance of it being in the corner. Okay, so that's going to be what we actually can aspire to find out: the probability of finding the particle. The last thing I'll say on that is that it's a wave and a particle, right? So if you think of what you're finding a wave that's being collapsed into a particle. So it's almost like the electron, when it's in some of these confined systems we're going to talk about, the electron being our stand-in for a particle, that it's doing its wave-like behavior and it's just sort of existing, right, in that trapped space. But as soon as we want to like find it, as soon as we interact with the system to measure its location, it's then like manifests itself as a particle. All right, because the very act of making the measurement is going to interact with the system, especially at such a small scale. There's no way to not affect the system through the process of observing it, and thereby we say that we collapse the wave function into a particle. But we never know exactly where it's going to be. We just know the chances of where it's going to be. All right. Okay, so that justifies our jumping into more, at least, into the idea of probability waves. Okay? Well, probability waves, yes, but it's not. The probability isn't waving. The probability function, is just kind of wave-like, because it's just the square of a wave function. All right. So to do that, we're interested in string waves and matter waves. String waves being just not like string theory at all, just being strings, like a string on a guitar, right? A string instrument. And what we're going to do with these we're not going to do anything with string waves other than just mention them as comparison. But what we're going to do with matter waves is we're going to confine them, all right? So confinement of a wave leads to quantization. In fact, it even leads to quantization at the macroscopic level. That's what we call like harmonics. Certain, standing waves have to have a certain number of nodes and so on. All right, that is to the existence of discrete states with discrete energies. The wave can only have those energies. So for comparison, right, like I said, just like harmonics on a string, the string can vibrate so that it has this shape, which would be a 1.5 wavelengths fitting within the fixed ends of the string. The string could also vibrate, so it has one full wavelength, or it could have a half wavelength, but it couldn't say have 4/3 of a wavelength. It couldn't have 7/9 of a wavelength. It can only have particular multiples. In this case, you can have you could add additional 1/2 wavelengths. So you could have for example 2 full wavelengths or 2.5 and so on, but nothing in between. That's quantization. Those are discrete steps of waves that exist, and each one would have an energy associated with it, which will certainly be the case with our matter waves. So this observation applies to waves of all kinds, including matter waves. For matter waves, however, it is more convenient to deal with the energy of the associated particle than with the frequency of the wave. So we're not interested in the frequency so much, because unlike string instruments, the frequency is the kind of the way that as humans are going to interact with what it means to have these different standing waves, because the frequencies are going to be the different sounds that are heard, right? Well, in the case of particles, it's not so much the sound that we're interested in. So, I mean, certainly not. It's the energy, okay? Because then the energy is going to be able to relate to things like, what you can do with that electron, and even ideas that we won't cover, like will the electron maybe tunnel, right? Which would be when the potential energy isn't infinite, but more on that in just a minute. And then we have another version of Schrodinger's equation, and this is the one we're going to use. All right, so we saw the free particle case, the free electron case, and the version of Schrodinger's, the free electron situation, and the version of Schrodinger's equation that applied to it. Well, here we have the trapped electron and the version of Schrodinger's equation that applies. This is a one-dimensional case, as you can see, because it's just a function of x. There is going to be a potential energy, all right? You'll see, and it's going to be clever what we do with it. And that's going to be the only version that we care about from this point on. There are some that I didn't show you that I only quickly mentioned in passing, like harmonic oscillators and so on. But this is the one that is a great start and a interesting version. Well, let's get into the different cases then, okay? Because I said that once we turn our focus to confined electrons, then we can look at 1D cases, 2D cases, and 3D cases. Well, it makes sense to start with the 1D case. The 1D case is pretty neat because you can really think of maybe actually doing this as in a laboratory. An electron can be trapped in a region where the voltage is zero. So imagine that you set up some sort of conductor or semiconductor, so you have a region where there is zero voltage, and then to either side of it, there's effectively infinite voltage that the electron has no chance to overcome. The electron is then absolutely trapped in that section of conductor. It cannot get out, okay? And in that case, it might as well be like a stringed instrument trapped between two fixed ends, right? Where you've tied the string down, which are called the nodes. That's the idea here. We have a trapped electron, and it's going to have a lot of the same ideas like the trapped string, right? So it's going to only have certain ways it can vibrate, or in this case, it's still the wave is right. The wave is moving about, and its amplitude is going to represent some physical quantity. But what we're going to care about is going to be a probability of, say, finding it in this half of our length, right? Because there's going to be some defined physical variable, right? So there's going to be always something like two sides or a single side, or in the case of a cube, three sides of it. So there's always that it takes up space. All right, and so you can't. It's not like we're just saying, we're confining the electron in zero dimensions. We're confining it in either 1, 2, or 3, and L is either a known value, or it's just kind of a placeholder. So it could be literally like 1 millimeter, or a few nanometers or something. And that length is related to the different energy levels, which are called the quantum number, but it's the same idea. They're integers, like we would see for harmonics. And it's then related to the de Broglie wavelength, and those are the only wavelengths, or rather, those are the only energy states that could exist. And the wave function solution that we're going to use for this trapped electron, whether it's 1D, 2D, or 3D, all of our wave functions are basically going to look the same. They're all going to be just a sine function. So it's going to be some constant, which we'll talk about in just a second. Hint, it's called the normalization constant. I usually use the letter C, but A is fine. And then times sine, okay? And it's just sine, right, of n pi. N is our quantum number, just an integer. L is our defined length. And then times our spatial dimension x, okay? So that's the solution. If we plugged it in, we could see, indeed, that it satisfies the equation. The equation, is true. Both sides are equal to each other. You can do it yourself for practice. All right? So the wave functions more on this idea of what it means to be trapped and how that directly relates to the idea of probability, which I think I've started to hopefully justify for you all. Well, the probability density, which again is just going to be the square of the wave function. In this case, they're not showing the absolute value. Not sure why. For 4 states of an electron, trapped in a one-dimensional infinite well are showing, right? And these are going to be 4 different energy states. So this would be the lowest possible energy state, second lowest, then n equals 3, and then a much higher one, n equals 15, okay? So these different, quantum energy states, the electron is most likely to be found where the probability distribution function is greatest and least likely to be found where the probability distribution function is least. In other words, in the case of the ground state, we would be much more likely to find the particle in the middle of our one-dimensional trap of length L than we would to either side. In fact, we have zero probability of finding it exactly at the ends, and obviously much less chance of finding it, say, near the corners than we would right smack dab in the middle. Okay, so what that kind of looks like to start our equation here, that means that the probability of detecting the particle in a width dx centered on position x is equal to the product of the probability density function at that position, so evaluated at that same value of x, multiplied by the aforementioned dx. Okay, so that doesn't really work, for math, because how do you multiply by dx? It's infinitesimally small. You could you can round this and you can make it a delta x, and as long as it's pretty small, you're essentially approximating that part of the curve as flat, almost like a Riemann sum method to work with an integral. So we could have a case where we have a small delta x, and then we're just finding the area of the rectangle, which would be the probability of finding it within that region, the approximate probability. But we're really not going to do that. We're going to integrate. Okay, so we're going to take that idea, and then we're going to say, okay, well, that's our probability function, all right, and it's equal to, all right, that product. And then we know that the particular wave function, which we came up with because it was the solution to this version of the Schrödinger's equation, which I didn't plug in and show you, but again, might be fun to do it yourself. Well, that's going to go in to our expression right here. So we're going to have to square it, and of course, then it's going to become a squared sine squared. All right, and then we're going to find a not approximate version, but an exact version by defining a lower and upper limit. Okay, so this could be any lower and upper limit. For example, I could say that like x I is somewhere here, maybe in this case like 25, and then maybe x f is over here at like 75, or anywhere, right? Or I guess I use 1 and 2. I could use x1 at 0, and then x2 at halfway, in this case 50, right? In that case, since I'm literally finding the area under the curve, since that's what the integrals tell us, I would just be finding that, and it would be exactly half of the total area. So what would it give me? Well, it would actually give me 0.5, because here's the thing. Since we're talking about probability, we have a neat assumption that makes a lot of sense if you stop and think about it. The probability has to have a total area of 1, because it's just saying that the particle must be somewhere, because after all, it's trapped and it can't get out. So that means that this total area, if we were to integrate it from 0 to 100 in this case, right, just arbitrary chosen numbers, that total area would be 1, always. And not just in the case of the n equals 1 energy state, but also for 2 and 3 and 15. Right, so every one of those areas, if we found the total area under the curve, whether it's one mound or multiple mounds, will always sum to 1. And that idea of the total probability summing to 1 is how we find the normalization constant, how this A doesn't just remain a value that you have to be given, but instead is a value that you find. And it also is going then to allow us to go that extra step to find specific probabilities that are less than 1, such as the one I said is 0.5, because you have half of a chance of finding it in either side of the ground state. All right. Now, it's you can tell it's symmetric, so it's got to be 0.5, but we could check it with an integral. All right. So what that looks like as an equation is that we would evaluate the integral from negative infinity to infinity, except we don't even have to be so vague. We can specifically say we're just evaluating it from the boundaries, because every one of the particles that we care about is imprisoned. It's always trapped. So our boundaries are always known. In the case of this one-dimensional trap, the boundaries would just be 0 and L. So that means our upper and lower limit would be 0 and L. Okay, so the negative infinity and the infinity is great, and it's still true, because this is just saying that the probability of the particle existing everywhere has to be equal to 1. But since our particle is completely trapped, we don't have to worry about it being outside of the trap. Okay, and when we do that, then we can ultimately, one of the main things that we want to do this for is then to find the energy levels. All right, because once we find the normalization constant, and then we can evaluate energy levels, or we can relate energy levels to probabilities, and so on. All right, so we're almost going to get to the last part of this lecture, where I'll just go over a couple of examples. So we're wrapping up with the key concepts here. So the energies of a trapped electron. Well, if we wanted to find the quantized energies, which I said is arguably one of the main takeaways, then you would the solution to the 1D case leads to energy states that have this nice form, which are just based off of quantum numbers. And this is just, you find the result like this just by going through the process of normalizing your Schrödinger equation and then evaluating probabilities. Or often, in some cases, if you're not interested in the chance of it being somewhere and you only want total energies, then really the key thing to do is just to find that normalization constant. So it kind of depends on what your final goal is. But with like any kind of common, or like with many systems of problems, there's sometimes you're asked different versions of the same sort of question. And one thing I wanted to point out, I added this figure over here, is that it's easy to get confused between the wave position function and the wave probability function. Okay, and I said that the wave position function isn't of much interest to us because our particles slash waves are inherently uncertain, so that we don't want to expect to just find them somewhere, right? It's not practical, and furthermore, sometimes it doesn't make sense, such as for the free particle. So that's why we're not interested in the exact equivalent to standing waves like those in a string, right, where they have nodes and so on. Instead, we're interested in the absolute value squared of that, which becomes the wave probability function. So in other words, when we look at this curve, this doesn't represent like a wiggling wave. It just represents a probability, right? So it's a more abstract graph in a sense, but it's also really closely related because it is, after all, just the square of it. And it holds some of the same ideas true, such as always being zero at the boundaries, whether it's the wave function or the probability function. And just to reiterate, the idea of the trapped particle is that you have some region where, and actually one thing that I haven't explicitly said, but I hinted at a minute ago, is that you have some region where the particle can exist, right? So the particle can be in here, right, waving around. I'll make a wave that actually looks real, right? There we go. Right, that'd be like an n equals 2 state, and that's the wave function, not the probability function. But that's our trapped particle, all right? And if we go to observe it, we find, oh, look, it's there. And a second later, we go to observe it, it's there, And it's just wherever the instant you try to observe it, you find it somewhere. But then you're not going to find it in the same place when you go and observe it again. So it comes down to that chance of where you'll find it, with greater chances of finding it in some spots than others. That's the probability distribution. And then this wall is infinitely tall. And that means that the particle can never get out. There is no chance of it getting out. And if you've heard of quantum tunneling, which I mentioned in passing also a minute ago, well, quantum tunneling does not apply here. Okay, a very similar system can be worked out, and it's covered in most textbooks that introduce physics in the lower division with calculus, but we don't have time to cover it here. And that's going to be a finite potential energy well, which is what this is called. Our trap is usually called a well because you can kind of see how it looks like a well depending on how you represent it. So when you have a finite one, so just some case where you got potential energy down here, and maybe a potential energy up here is big, but it's not infinite. Okay, well then there is a chance of tunneling, which doesn't happen for macroscopic particles, but is common with quantum mechanical particles, tiny things, and it helps explain things like radioactive decay and other worldwide phenomenon. Okay, that's not what's going on here. Here, it's totally trapped. There's no chance of it getting out. And that allows for a great mathematical simplicity or simplification. We can actually set the potential energy at the bottom of the trap as 0, which is actually the same potential energy that made working with the free particle easy, because we could set that one equal to 0 as well. But when we evaluated the probability distribution, we just found a constant in that case. We're going to find here more interesting things. But what's great is that we can still set that whole term to 0, just as a choice, right? Because it's just one fixed value, and then outside is, there's essentially, there's no chance of going there, so we don't have to worry about it. And so we're just conveniently defining our constant potential energy as 0 within the well. all right? Because that's how potential energy works. You set your reference. In this case, our reference is the well. Hey, might as well call it 0. All right. So we got an example here where we're going to be looking at the probability of finding the electron in a ground state, so an n of 1, right? That's the quantum number, in a one-dimensional box with a defined length. And you can go ahead, you can see that they just, take a look at the integral. And actually, we're going to probe the left 1/3 of the well, right? So it's the idea that we're going to find out what's the probability of finding the particle over here, but not in the rest of it. Well, when you evaluate the limit or evaluate the integral with the limits that correspond to that question, so in other words, a lower limit of 0, which would be like the entire far left side of the well, to a value of L/3, then you get a result of 0.2. In other words, you have a 20% chance of finding the particle in the left 1/3 of our one-dimensional trap. All right? And again, if you were to do 0 to L instead of L/3, you would get 1 here. You have to. And the reason that I know that it would work here is because the normalization constant has already been given. All right, this is the easiest one to find, the normalization constant for a one-dimensional trap. It's just 2 over L. Okay, but regardless of it being the easiest one, it's given to us in this case, and it's then going to allow us to easily find any probability, including checking that the total probability is 1. And it's all probabilities, right? But you can change them to percentages, and I do that readily, right? So I say, oh, it has to be a probability of 1 of being found somewhere. That's the same as saying there's a 100% chance of finding it somewhere in the trap because it can't be anywhere else. All right, so enough on that example. We got one here where we look at what does it mean to normalize a function. So there's some excellent questions here that really kind of challenge your understanding of it. I'll take a quick look at one of them. So A, what does it mean for the wave function of this particle to be normalized? And this, what particle are we talking about? Well, it's up here. Consider a particle moving in one dimension, which we shall call the x-axis, okay? Well, if we, want to ask, in one dimension, as we have here, the integral discussed above is of the form, right, evaluated from -infinity to infinity, and it has to be equal to 1. So that's what normalization means, okay? So then, if we want to say that this is our wave function, all right, now this is not a typical wave function for a trapped particle. The one that we're always going to be using is, you saw it before, it's the sine, right? It's this one right here, right? It's just going to be a sine of n, just integer, pi over L times x, okay? That's always going to be our chosen wave function. It's excellent one to work with. And so they're asking here, well, could we use this one instead? Is that a valid wave function for a particle trapped in a box? Well, they go through and they ask themselves, can they normalize it? And they can't, because when they actually evaluate the limit with the very stringent requirement of going from -infinity to infinity, they find that the result is not a constant. It has to be. It can't be infinity, right? Or undefined, and it's infinity. So that means that particular wave function is a bad choice because it is not normalizable, which means it cannot represent a physical wave. Okay, you can use it for math, but you can't use it for physics. And then that's kind of the idea. And then with C, they say, well, what if you restrict the particle to only be in the positive side of our infinite domain? And in that case, it actually does work, because when you solve the integral, you get a fixed value, which tells you that your normalization constant, if you solve for it, is just equal to the square root of 2b. And notice the method here, right? Because we always, when we want to normalize something, we assume that it is normalizable unless we, find out otherwise. Because essentially what was found here was that 1 equals infinity, which of course is not true, all right? Because you have a 1 over here. Well, here we're going to do the same thing. Say, okay, we're going to assume that 1 equals the result of our integral. And here they didn't write it because I guess they probably knew it was going to be wrong. So the 1 doesn't even show it. But here we're going to make that assumption that it is normalizable. And then we get over here and we find out that it equals a constant. And then we just solve for A, which is the normalization constant. In this case, B is just some other constant, some other, represents, I don't know, H over M or something, right? And so, but the fact that it just equals a constant is enough. It tells us that we found our normalization constant, and then we could go on to find the probability of the particle existing in particular regions. Okay, so it's like first find the normalization constant, if it's not given, and then use that to find out the probability of further restrictions, right? What's the chance of it being in the middle? What's the chance of it being in the corner, like I said? Okay, we got another one here. Probability of finding a particle in a box of length L. And sometimes if the terminology throws you off. Box here is a one-dimensional box, which is a weird idea, right? I tend to use that if it's one-dimensional, I just say that it's in a well. If it's two-dimensional, it's a corral, and if it's three-dimensional, it's a box. Okay, so I use different words for the different 1D, 2D, and 3D cases, but a lot of sources don't. Okay. So yeah, so here we have a one-dimensional box, and we want to find the probability of finding the particle between L over 4 and 3L over 4. So essentially finding it in the middle half, right? So just excluding the extreme, 1/4 on one end and the other quarter. And when we go through that process, let's see, because that's part A, just want to quickly show you the result. We get 0.818, right? So nice result there. So you have an 81.8% chance of finding the particle in the middle. And let's see what energy state are we in here? Probably the ground state, right? When the particle is in the ground level. And that makes a lot of sense, right? Because if you go back to your picture over here, that's saying that, what's the chance of finding the particle, from here to here? Well, that's most of the area, right? Because we're just excluding the, 1/4 on either end, which I probably went a little extreme there, but something probably like that, right? Well, that's most of the area under our probability curve. So that's why it's so large and such a high percentage of 80, right? And then furthermore, in the second part, in part B, they say, what about in the first excited state? Well, in the first excited state, it becomes less likely because, as you saw, then you have the two mounds, and you don't have such a bias to finding it in the middle, right? So that's why the energy states can matter in terms of actually working with what our probabilities are. So see that, right? That's our last idea where I said that what you care about is the size of the prison, right, or the size and shape of the prison. Well, you're seeing that's really all you need to know. You just need to know how big your trap is, what part of the trap you're looking at, and the last part is you do need to know the energy state most of the time, well, practically all the time. All right, so it's the one. It's a little bit of a lie to say that we only care about the size and shape of the prison. We also care about the excitement level of the prisoner. Okay. So a little bit more about energy levels, right? So you have like your ground state energy level, first excited, and so on, right? They all have actual different values in joules, or more appropriately, electron volts. And at the end of the day, that is one of the main things you care about, right? But then those different energy levels affect the chances of the particle being in particular spaces. So you can kind of relate one idea to the other. All right, so more about transitioning through energy levels and how that corresponds to an input or an output of energy, such as the absorbing and emitting of a photon, just like what happens in atoms, right? So you can see that as you scale this up and you make your system be three-dimensional and then you make it spherical, then it becomes a really nice system for thinking about at least the hydrogen atom and thinking about absorbing an electron, or rather absorbing a photon, which excites your electron to a higher energy level. And then when your electron relaxes, it has to emit a photon of the exact corresponding amount of energy, which then will correspond to a particular color or wavelength of that photon, right, of the light. Right, here is the two-dimensional case that I promised you earlier. In this case, the normalization constant was already found, but here's where things add like the final wrinkle that you're going to see. Well, this is a square. Well, what if it wasn't? What if it was a rectangle? What if one side was L, but the other side was 2L, right? Or rather, this side was 2L and the other side was L, right? If I had 2L and L. Well, now our normalization constant wouldn't be the same for both X and Y. Right? So for this particular case of this two-dimensional square trap, the corral, well, then, this is such a common case that they often give you the normalization constant already, but one of the assignments that you'll have to find it for a rectangle. Not any other shapes, by the way. You won't have to worry about, triangles or circles or anything. We'll just stick to rectangles. And then finally, the three-dimensional case. Same idea here, and even our picture implies it, that the three-dimensional trap, the three-dimensional box that cannot be escaped from, these are impenetrable walls, right? They're infinitely thick. Well, it need not be a cube, right? And so that means that the normalization constant that we find is going to depend on the particular shape of the prism. All right, especially good wording for this three-dimensional prism. And one final example of a case, of a three-dimensional case, where we do have a cube, and you can see that we're asked a question about the probability of finding the particle in a particular region. In these, see, in part A, we're just asked to find the normalization constant, which is a good setup question. And then the reason we want to do that is basically what's asked in part B, for example, which is find the probability that the particle will be found somewhere in the region defined by x between 0 and L over 4 for the cases of this particular energy state, and this one as well, and this one over here. And if you're wondering why the energy states are suddenly now not just an integer, but a set of integers, that's because it's three-dimensional, right? So in the one-dimensional case, it's just, there's only a single quantum number. In the two-dimensional state, there's two quantum numbers, one for x and one for y. And then in the three-dimensional case, it's a set of three quantum numbers. So then so it's a lot more quantum states as you get up to 3 dimensions, but it's still just, an integer for each dimension. Okay. So like, for example, this would be, the n of 1 in the x direction, n of 2 in the y direction, and n of 1 in the z direction. And that would be it's essentially a first excited state, right? Because only one of them has gone up 1 from the lowest possible state, which is 1, because you can't have a quantum number of 0. And when you have your nice cube here with all its beautiful symmetry, you find that the normalization constant is equal to the cube of 2 over L, all right? Or actually, the square of the normalization constant is equal to the cube. And the normalization constant itself, I'll zoom in a bit here, the normalization constant itself is equal to 2L raised to the 3/2 power, okay? And so that's great, and it's a great result, but don't count it to apply for every three-dimensional trap, because it only applies to the cube. And also, there are a lot of cases of with three-dimensional rectangular shapes where the normalization constant is nice and clean like this. But then there's other cases where the normalization constant is a function of the energy state. So it depends on kind of how symmetric your box is, or like are the lengths, the side lengths of the box, if it's not a cube, are they like nice multiples of each other, or are they just kind of like random lengths? Because in the case where they're lengths that aren't nice multiples of each other, then you have an extra dependence where your normalization constant isn't just one fixed value, but it will only apply to each energy. Okay, so that'll be something to look out for in the homework. All right, so hopefully that wraps up everything nicely, and you feel like you have a good introduction and a good start on this subject. Thank you for watching this video.